and let's just go with it, if that's okay. And also, I wanted to say I hope you everything went well last week, and that it was sort of okay for you to not to have lectures, and that you could focus on your midterm in real analysis and so on. Okay, so let's recall what we did last time. So let's see, take some color. And please tell me if you cannot hear me or if I'm writing okay. So it seems to be okay. So from last time, we proved Cushy's. So we proved Cushy's theorem on the disk, but we also proved Cushy's integral formula, right? So if you remember, this was a representation formula which said the following: that f of z was 1 over 2 pi I integral along gamma f of omega, or f of w, sorry, w minus z dw, where gamma is a closed curve, okay, and in some domain where f is holomorphic. And this was also assuming that the winding number of z in this curve gamma was equal to 1. So remember, the winding number, if you had some curve here, it meant it was winding around z exactly once, right? So you have this concept of the winding number of a curve. So we had this formula, and then we also showed that we had higher derivatives. We proved these formulas, if you remember. So higher derivatives we had, for example, we could write by simply what you would expect, so that you would differentiate under the integral sign here. So you would get f prime of z would be equal to 1 over 2 pi I integral, and now we can take c here to be the unit circle, winding exactly once around z, and then it would be equal to f of w over w minus z squared dw, and so on. And if I now replace this, so if I can replace this prime, I can write instead the nth derivative. Then what I had to do is I had to put an n prime here, and I had to change this one. So then you put n factorial, sorry, n factorial, and here you put n plus 1 dw. And c here was the unit circle. Well, the circle, it's a circle around, circle centered at z, winding around exactly once. Okay, so we want to have this winding number set equal to 1. Okay, so we had these things, and then we concluded that this meant that analytic functions are infinitely differentiable and their derivatives are analytic. So analytic holomorphic functions are infinitely, so I'm using, if it's okay, I'm abbreviating a bit more than I would on the blackboard, right? Because it takes some more time to write with this pencil. So they're infinitely differentiable and their derivatives are also analytic themselves. Okay, and they are given by the above formulas. So it's given by this formula.
Hello, sir. Can you hear me?
Yes, hello, I hear you well.
I still have a question about, I still think that for analytic function, we should be doing this for holomorphic functions, because for analytic function, I still think that we can prove it without using Cauchy theorem.
Okay, yeah. So when I say analytic, I really mean holomorphic in some sense. So after the course is done, you will know that analytic and holomorphic.
No, I mean at this point, before knowing that they are the same thing.
Yeah.
I think because analytic function could be proven to be differentiable without using, I mean, just from the formula and calculus we can get.
Yeah. Okay. Yeah. So you're right. So by analytic so far, I guess I should have been careful about that. So in my mind, they are always synonymous, of course. But I mean, I never really introduced in this course what analytic should mean unless it means holomorphic, actually. So whenever I said analytic or holomorphic until now in this course, I meant holomorphic, actually. Today we will prove, however, that holomorphic functions have a power series expansion at every point, which is what it means to be analytic, right?
Okay, yeah.
So after today, I will really not be cheating when I say analytic instead of holomorphic, but you're right. So if you want, I can, okay, analytic function, holomorphic function. Good point. Thank you for the remark. Okay, but so anyway, so this point is kind of important, that analytic functions are infinitely differentiable and their derivatives are also analytic. So what it means is that if I can find a primitive function, if I'm given a function and I don't know if it is holomorphic or not, I can find a primitive, and the primitive function, the antiderivative, is holomorphic, then I know that my original function must also be holomorphic. Okay, so this is the idea behind the proof of Morera's theorem, which is a converse to Cushy's theorem. Okay, so we have a converse to Cushy's theorem. And by Cushy's theorem, I'm not talking about the integral formula, but the Cushy's theorem for a disk, which said that the integral along a closed curve is always 0 if the function is holomorphic everywhere inside and in the neighborhood of this curve. So this is so-called Morera's theorem. Okay, and it says the following. So it says that, so suppose that f here is a continuous function. So we're not assuming holomorphic, right? We're just assuming that it's continuous. So on this domain, so on some open connected region, U inside C. So I was never very careful about saying, what exactly does it mean to be a domain, and does it need to be open, does it need to be connected, and so on. Okay, but on this open connected set. And then the theorem says, so the converse, as I said, to Cauchy's theorem, which would be what? It would be that the integral, so if the integral of f along a curve gamma, so if it's 0, but for all closed paths, gamma in U. Okay, and then f is analytic, but thanks to the remark here, I will instead write then it is holomorphic. It's also analytic, but it's holomorphic. This is what I mean now. And it's holomorphic on this set U. Okay, so we have this converse, this Morera's theorem. And now let's try to prove it. So let's try to go with the proof. So for the proof, so the goal, thanks to the remark we made earlier from Cauchy's integral formula, we show that f of z, so we want to show that f of z is holomorphic, right? So we show that f of z is the derivative of some other holomorphic function, capital F of z. And then this will imply that f of z is holomorphic as well. I hope these abbreviations are okay. Holomorphic function f of z. Okay, so how do we find this antiderivative? So the way we are going to do it, of course, it's going to involve some kind of integration at some point or another, as usual. So what you do is the following. So you fix some point, and then you consider following triangle. So for each z in U, we want to consider the following. So let's take some point here, which could really be any point, but let us assume that it's 0. So, and if it's not 0, then you can just relabel this point 0. This is just a topological argument, so it doesn't really matter. Okay, sorry for that triangle. There we go. So this is Z0 and this is Z. Okay, so you fix Z0 and then you take, for any Z, you can look at such a triangle to a third point, 0. And then let me explain what we want to do. Then we set, so the candidate, what would be the candidate antiderivative of this function f? Well, it would be something like, if you think about real analysis, you have the fundamental theorem of calculus. So if you integrate f of omega d omega along some, you would put some interval. This is what you would do in real analysis. You would put 0 here and z here maybe, right? So now in complex analysis, the way I will write this is just I take this line segment and I take 0 z like this. So I look at this along this line segment here, and I consider this integral. And now I want to see what this one equals. Well, we have, first of all, we note now that f of z is equal to, so this was the definition, right? And then f of z minus f of z0. Now let's look at that. So f of z0, it's the same thing, but we put z0 here instead. So f of z minus f of z0 is equal to the integral from z0 to z of f of w dw. And why is that? Okay, why? Let's see if someone can answer this question.
Because it forms a closed bus and the integration over the closed bus is 0.
Exactly, thank you. Yes, so this is exactly right. So the reason is that the integral of this function over the all of this triangle here is equal to 0, and this is by hypothesis, right?
But how do we guarantee that the triangle is in U?
Is in U? Yeah, so your worry is that this 0 might not be in U, or that U might not be convex or whatever, so that this triangle is not in U. Yeah, so what I said, so this 0 is really just some kind of notation.
Yeah.
You know, if I choose any other point, which is not 0, then I will just change, I mean, I will pick up by the fundamental theorem of calculus the value of f in capital F in 0, right? Or in whatever point I choose. And with this, all of these choices will just differ by a constant, and it will still be an antiderivative. So this is sort of a moot point in this.
I think if we take Z sufficiently close to Z0, we can say it's convex when it's really close, because they are all in the same ball or something.
Yeah, but I mean, you could also argue that maybe 0 is not even inside U to begin with. So it's really important that we can take
point instead of 0. Yeah.
Yeah. So we choose some point.
Because we are gonna derivate it, so we need them. It's okay to take them close.
Exactly. So all of these are, this is a very local picture of this whole thing, right? And we are just looking in some very small neighborhood around this thing, where we're in U, which is an open connected set. So we can always just have a work inside a very small but disk or something like that, right? And everything is nice there, and everything goes through. So now let's see. So now we want to use that f is continuous. F is continuous at z0. Okay. So this implies that if we just write down essentially what it means, so for every epsilon, there exists a delta such that if we are close to z0, then the function values are also close to each other. Okay, first year stuff. So what does this mean? So the conclusion now is that, I mean, what do I need to choose, right? So what do I need to do? I wanted to show that capital F was the, or was a antiderivative of small f. So what I need to do is basically to look at this kind of quotient and then see what happens here, right? Or rather, I want to show that it's differentiable, and then then its differential has to be f. So this is equal to absolute value of this. So now just writing down what this means, again going back to the definition of capital F. It was given by such an integral. And now this is so this is less than or equal to epsilon over. So now I'm using this here, right? To say that, oh, sorry. So this should be right. So what I do is I put the absolute value inside here, right? So I can always put absolute value inside, and I forgot also to end this absolute value here. But if I want, I can put the absolute value inside. So I do all this in one step. So this is less than or equal to this. And times this. And now what is this equal? Well, actually, what I pick up from the integral is just the length of this line segment, which is exactly equal to this. So it means that what I get is simply epsilon. Okay, so this means that f is differentiable at z0. And what did we know? So we had that. So by construction, so to speak, we should have this, and this implies by the remark that I had up here that if we can show that f is the derivative of some holomorphic function, then this derivative has to be holomorphic as well. So this means that f of z is holomorphic. So it's holomorphic at z0, so it's complex differentiable at z0, but this z0 was arbitrary, so we can do this local argument around any z0, and then we would be done. And this would then prove Moreira's theorem. So it proves the converse. So it means that if you have an analytic function and you have a closed curve, then, I mean, with all the hypotheses that we have spoken about, then the integral has to be 0. But conversely, if you have a continuous function, so you saw that we used the continuity in the proof, right? So this is the important hypothesis to remember. So if you have a continuous function on a domain and all of the integrals around any closed curve in the domain are 0, then actually your function must be holomorphic. You have no choice. Okay.
Professor.
Yes.
Professor.
I'm still confused about this absolute value operator around dw.
Yeah. So this means the sort of length measure, right? So if you take gamma some curve and you integrate it against this, then it's equal to the length of gamma. So
Okay.
the way that we used it here, I mean, so first of all, when you, so by some, I mean, the inequality is trivial, but if you have something like this, right? So you have absolute value of some integral, then is it okay that this is, to see that this is less than or equal to the absolute value of whatever was here times the integral and the absolute value of whatever is inside, but I always have to put also the absolute value on this, otherwise
It would be 0, right, Professor?
sorry?
Because one is analytic and it would somehow be, because the constant function is analytic, so it would be, the integral would be 0. If that's some other reason. If we didn't put absolute value sign on dw.
Yeah. So you're saying this integral here, you're saying this should be 0?
No, that's not what I'm saying. If
Yeah.
we didn't put absolute value
Yeah,
sign
yeah,
around dw,
yeah.
then it would be
Exactly.
0.
Yeah. So if you, so if you don't put the absolute value, then this kind of inequality here is simply wrong. And exactly for the reason you say. I mean, if gamma is a closed, yeah. Yeah, I mean, for this kind of inequality to hold, I mean, it's, if you think about it for 1 minute, you really see that you need to pick up the length and you need to not pick up this kind of integral along a closed curve of a constant, which as you say, would be 0.
Professor, I have a second question.
Yes,
We said in the earlier lecture that if a function is holomorphic inside a certain domain, then we can write it as a Cauchy integral formula. We can express it by a Cauchy integral formula. Is the converse true as well? If I can somehow represent some function in the similar representation as Cauchy integral formula, then is it holomorphic in some sense?
So you're saying that if a function f of z is equal to this, then is it holomorphic?
Right.
Yeah. So then I would refer you to, I would answer in the following way. So I would refer to the exercise, whatever it was, 4 or 5 or something on your homework sheet, if you remember. So when we proved Cushy's integral formula, there was this lemma that was missing. I have it here in my notes, so I don't know if you can see, where's the camera? So like probably maybe you can see, you cannot see. You see, there was this lemma anyway that said that if you have an integral of this form, then it's differentiable in complex sense. Can you see this?
I don't know how to work this. Sorry.
Yeah, but so what this lemma is saying is
Yes.
anyway that if you have an integral of this form, right? Yeah, if you see my camera now, of course, it's what
Right,
I'm showing.
right. Yes.
Right. Yeah, so if you have an integral of this form, then it's actually complex differentiable. So it means, yes, that if you have some representation like this, then you can differentiate it in the complex sense. Hence, it satisfies the definition of being holomorphic.
Okay. Thank you, Professor.
Okay. Very good.
Thank you, Professor.
Professor, I have a question in the proof.
Yes, absolutely.
We had the absolute value of capital F of Z minus capital F of Z naught.
Yeah.
We defined the capital F to be the integral from 0 to Z F of omega.
Yes.
Okay, so we have the integral from 0 Z on 0 Z F of omega d omega minus the integral 0 Z naught F of omega d omega.
Mm-hmm.
Okay. Why we have F of Z naught?
Sorry, so your question is why this is true, or I didn't get it?
Not this one. Down. You know, that last line now. Hence, the absolute value of F of Z minus why this is equal to that, this integral.
Why this is equal to this integral? Okay, so we want to know this equality here.
Yeah.
Okay, this is the question. Okay.
Yeah, I don't know why we have minus F.
Why we have minus F of Z0? Why we have minus F? Yeah, you're right. You're right. Wait, hang on. It's because f of z0. Yeah. So now, again, I wrote this over a week ago now. So let's see if I can remember why I wrote it. But f of z0, it has. Yeah, you're probably right.
Now we have to subtract fz0 and add fz0.
Sorry, come again. The sound was lagging a bit. Sorry.
Maybe if we subtracted the fz0 and added fz0.
We subtracted fz0 and added fz0.
Because that's going to go to, now that this one is going to be to 0, it's less than epsilon.
Right.
And the other thing is what's going to give us the derivative.
Right. Yeah, you're absolutely right. Yeah, so the explanation is that, yeah, I had already forgotten this in this week, that we didn't have course. So what we did is exactly what he's saying, that we added and subtracted f of z0, and we actually, it doesn't change the value of the of anything.
We can't hear very well. There is this echo. I don't know.
Sorry?
There is an echo.
Yeah, I know there is an echo. I don't know what this. I agree. It's a bit hard. I don't have any sound on my iPad, so it's not because of this. Yeah. I don't know. Yeah. Can I go on despite the echo?
Yes.
Okay.
Yes.
So Hagar, I hope yeah, the explanation for this inequality, or for this equality here, is that you add and subtract f of z0 first.
Yeah, but this is like the modulus of f of z minus f of z naught over z minus z naught. This is the derivative. It doesn't supposed to be 0.
No, but I mean this whole thing is not going to be 0 just because of it. But okay, maybe we can come back to this after. I mean, then we can write down maybe what it means. We can fix that.
Okay.
Okay. Sorry. So, okay. So let's move on. So what we are going to do now is we're going to look at some further consequences of this Cushy's integral formula and of all of these things. So it has some sort of collection of standard but nice applications. So Cushy's estimate, Liouville's theorem, and a simple proof of the fundamental theorem of algebra. So this is what we're going to do quickly now. Okay, then we'll go back to this Morera, look at this proof at the end if we have time. So the first one here is the one that's called Cushy's estimate, which is a very useful one. So Cushy's estimate says that, so what it is actually, it's just a bound, and it's something very trivial, which you can just do naturally without even knowing it has a name. But so what it is that you look at bounding this nth derivative of some holomorphic function. So I'm not going to write every time, okay, but the function is holomorphic here. So then this is less than or equal to this times 1 over, whoops, something on the screen. Okay, times 1 over Rn, where I have to tell you what this MR is, where MR is the maximum over this disk of radius r, not the disk actually, but the circle of radius r, sorry, of the absolute value of f of w. So this is an extremely used estimate in complex analysis, and the proof is very straightforward. So the proof goes as follows. So we look at this circle. I wrote here in my notes a plus r e to the it, but I guess that can't be right. So it must be probably z plus r e to the it. T is in 0 to pi. Okay, so what we do is we simply take a circle around z, I guess. Okay, of radius r. And then we look at this, then we use Cushy's integral formula. So at this step, we use Cushy's integral formula. And we get that this is equal to, so the absolute value here just tags along for now. So it's the integral of this. dw. And then we do exactly what we did earlier, that we put the integral, the absolute values inside. So the absolute value of 2 pi I, which will be 2 pi. Okay, but let me put it like this for now. Absolute value of f omega, or absolute value everywhere, I put the absolute value, including on this measure, which will now be the length measure. So again, I mean, why is this true, basically? So if you just think about when we do this kind of estimates in real analysis, just since we had a question about this earlier. Okay, so then you have a function which can take positive and negative values and so on. In this case, this kind of integrand, of course, it takes complex values, so it's a little bit different. But anyway, when you put the absolute value over the integrand and you want to estimate it, then what you're saying is basically that the bound you get is by you can put the absolute value here, and then you put it outside, and what you want to integrate against is, of course, the length that you go around. You don't want to integrate against something that becomes 0. So I mean, I don't know if I'm explaining it very well, but it's really it's really necessary to put this absolute value, this length measure of dw, because this is really what the estimate is about. I mean, in the simple prototype, just imagine f of w, this integrand took positive or negative values, and then when you put the absolute value inside, well, I mean, you have to integrate along the path, the length that you go around. Okay, I don't know if that was very clear, but that's how I think about it anyway. And then let's continue this estimate. So this thing here is just 2 pi. So now I write 2 pi. Then we have the integral. Yeah, and when I have the integral, this whole thing here now. So yes, so when I look at this thing, so the absolute value of w minus z, so w is on the circle, right? So w is here. So it means that absolute value of w minus z is equal to capital R, is equal to this radius. Okay, so what we get over this is the maximum over this circle of the absolute value of f omega divided by Rn plus 1, if you want. But of course, this thing here, the Rn plus 1, it doesn't depend on w in any way. So I can put it outside just as well. So let me erase it and write the maximum of f of w like this, times 1 over Rn plus 1. And then what's left is this integral of the absolute value of dw. And this thing here is, of course, just equal to 2 pi capital R, because it's just the circumference of this circle C. So putting this together, then we get that this is equal to n factorial, and what we had here, remember, this was exactly the mr. We call the mr, if you see at the top of the screen there. And then I have 2 pi r and 1 over Rn plus 1. So yeah, the 2 pi canceled here, so you get this and you get r to the power minus n, or times 1 over rn. And this is what we wanted to prove. So this has a name, Cushy's estimate, but actually, I mean, it really is something that you can do by hand, and you can redo it every time. So I don't think it's something that you need to remember. You know, okay, what was exactly the formulation of Cushy's estimate? Well, you just learn how to do it. That if you have this kind of integral, you put the absolute value inside, you consider the maximum of this function along the circle, let's say, where you integrate, or along the curve where you integrate, and then you get a very similar kind of estimate, right? So, are there any questions about this one? Okay, so if not, then we can go to the second one, which is a very famous theorem in complex analysis. I'm sure many of you know it already. So the next one is Liouville's theorem. And okay, so for Liouville's theorem, let's recall that function, so this is a useful remark, is said to be entire if it is holomorphic on the whole complex plane, or if you want, on the entire complex plane. So this explains the terminology. So for example, for example, e to the z, sine z, many others, okay? These are all examples of entire functions. And then the theorem by Liouville, as I'm sure you know, says the following. It's a very catchy theorem, which says that bounded entire functions are constant. Okay, so this is a very useful one, a very nice one. So for example, the entire functions that we know here, e to the z or sine z, they are not constant in particular, right? I mean, they are not constant, of course, but this means also they are not bounded. And we saw this indeed. I mean, sine z, you know, we used from the calculus in real variables, that the sine and cosine function and so on should be bounded, periodic and bounded. But we saw that in complex analysis, it's not. And just another aspect of this is that it couldn't be, because otherwise Liouville's theorem would say that they had to be constant. Okay, so this is kind of a cool theorem, that there is no way to be bounded on the entire complex plane if you're a holomorphic function. This is simply incompatible. So let's see the proof of this. So the proof says that, okay, so suppose, so it should be an entire function now. So this is why I write from C to C. Is holomorphic. So it's entire. And assume also, of course, that it's bounded, and we will write this bound by M for any z in the complex plane. So we have a uniform bound by M. So now we will use Cushy's estimate. So the one that we just proved. So by Cushy's estimate, again, we can look at f prime of z. So this is less than or equal to, so let us recall, just go up for just 1 second. So then it would be, so n here would be equal to 1. So n factorial would be 1. Then we would have a maximum here of this function, and we would divide by 1 over r, right? So this would be, and the maximum actually of this function, well, it's less than or equal to m in particular. So by this Cushy's theorem, this is less than or equal to m divided by r. Okay. Because of course mr, this thing is, this maximum is less than or equal to m. Okay. In Cushy's theorem. But now what do? We notice that this is true for all r. Well, let's say for all r. Yeah, for all r positive. So then what does it mean? So if you have this estimate that there is some uniform constant, always the same constant m, such that f prime of z is less than or equal to m divided by r for any r, then it means that we can let r go to infinity. And this will then imply that the absolute value of f prime of z is always less than or equal to any positive epsilon. And of course, it's not a negative number. So there is only one choice. So in the end, we get that f prime of z is equal to 0. And now, how can we conclude? So we showed that the absolute value of f prime of z was 0. But then we use again this standard fact and complex analysis that if the absolute value of a complex number, so this is a complex number of absolute value 0, then it means that the number itself has to be 0. So it means that f prime of z is equal to 0. And then what does this mean actually?
That the real
This means that f is constant.
Okay, so I heard very well what Hagar said. It means that f is constant. Exactly. So was it Younes? You had a comment as well?
Yeah, the same.
Yeah, okay, it was the same. Very good. Yeah, so for some reason there is some lag on your sound, but so sorry about that. Please be patient. Okay, so this means that f is constant. And so this ends the proof. So it's not harder than this, right? So once we established all these things, so once we established the Cushy's integral formula with these derivatives, then we got Cushy's estimate very easily in a few lines. And then in another few lines, we got this proof that of Liouville's theorem, which says that bounded entire functions are constant. Okay, and as a third application, so let's see, get a simple proof. So Liouville actually gives an easy proof of the fundamental theorem of algebra. Okay, and the proof is the following. So how can we prove fundamental theorem of algebra? So remember, it says that any non-constant polynomial has at least a 0, right? So what we do is we pick some non-constant polynomial with complex coefficients, and z is the variable. So I know in the first lecture I said something wrong here. I said non-zero, but Younes pointed out that it was non-constant very quickly. Okay, so then P of z is equal to, okay, I just write down the polynomial. And the leading coefficient an, I assume it is non-zero, sorry. So, shit, what happened? Okay, apparently I stopped.
I think the connection on your iPad is very bad.
It's very bad? Okay.
Because it was, yeah, because the picture was very late and then it gone.
Mm-hmm. Yeah. So what on earth is happening now? What is going on? Yeah, so okay, so again, so this iPad, it's connected to the edu roam at ICTP, so there's not so much I can do since I'm here. Okay, so start the thing. Okay, then let's go here. And they're laggy, yes, indeed. Okay. But we are back, I hope. Yeah, I'm really sorry for all these technical issues. I mean, it's terrible. I know. We're doing the best we can. Okay, so now assume for contradiction. So assume for contradiction that P of Z is never 0. So this polynomial never vanishes. Okay, so what does this mean? So probably some of you have seen already this proof. So do you remember the trick?
1 over P.
Ah, very good. Yes, say no more. Okay, so 1 over P of Z is then entire. This is the point. So 1 over P of Z is entire, and so 1 over P of Z is then bounded, right? So this implies that the absolute value of 1 over P of Z, which by the way is just 1 over absolute value of P of Z, this one is bounded for any Z. And to conclude, now we use Liouville. So by Liouville, this implies that I mean, what does it imply? It implies that 1 over P is constant, right? But 1 over P is constant means that P is constant. And this is a contradiction, right? This is a contradiction. And we are done. Why is it a contradiction? It's a contradiction because I assumed that P was non-constant. Okay? So this is the proof of this result. Any questions about that?
I have a question.
Yes.
Why is 1 over P of Z bounded?
Why is 1 over P of Z bounded? So yes, yeah, you're right. You're right. So to see that 1 over P of Z is bounded, you probably had to do some computation. So actually, I shouldn't. What I should write. So this is a sort of claim. So this one is bounded. So let's see if I can remember actually. So what was the argument here? So it should be
If it's
something
not
easy.
bounded, then PZ goes to, there is a sequence such that PZN goes to infinity to 0. But if that sequence is bounded, then it has a limit point, which contradicts the claim that P has no zeros. And if it's unbounded, this is also a contradiction, because when it's unbounded, the norm is gonna go to infinity of the polynomial.
Yeah.
And not to 0.
Yeah. So with regards to your question, so yeah, so thanks, because what I wrote wrong was this part that I wrote implies here. I mean, it's much more correct to say that it's a claim that is bounded. But let's say that it's an easy exercise. I mean, so as was explained here. So it's very easy. I mean, I assure you, it's very trivial. But you have to write write the line, I guess. Oh shit. What is happening?
The iPad is lost again.
I think it's maybe overheating actually, because it still has internet.
I think it's maybe overheating actually, because it still has internet.
It's connected, but there is no picture.
Yeah, I know. I will try again. Okay. Okay. Yes. Yes. Okay, so this was kind of intended as some panorama of some quick results that you can get. And now I think it's completely lagged actually, because I'm writing something, but you're not seeing it. You're still stuck on the Liouville screen, or on the fundamental theorem of algebra screen. Okay. Now you see.
Now we can see.
Okay. Yeah. Now you can see. Okay. Good. Okay. So if you remember now that when we proved Cushy's integral formula, it's very annoying. I can hear myself with an echo here. Okay. Let's see. But can you hear me okay, despite all this echo, or?
Yeah, we can hear you.
Okay. So when we proved the Cauchy's integral formula, we used this generalization of Cauchy's theorem for functions with removable singularities. I don't know if you remember this, since it was some week ago now. But at some point we used this.
We lost the iPad.
Yeah. Okay.
We lost the iPad again.
Okay. So let's see what we can do about that. Maybe I let the iPad rest for just 5 minutes and it can cool down a little bit. Maybe, I don't know.
Maybe you can write on the blackboard.
We can see the board.
You can see the board. Okay, so let me write on the board and let's see if it works. Which part of the board can you see? If I start, probably here is the limit point, right? Okay, so I will try to write big and talk loudly. No, can you see anything? You can't see anything, right?
We can.
You can?
We can.
Okay, let's see. Let me click here.
It's very pale, but we can see.
Okay. Removable singularities. Okay, so the definition of this if you remember, it was that if you have some holomorphic function which is holomorphic except at some point, okay, so you have some u, you have some point inside where maybe it's not defined. You cannot see all of that. Is it better? Is it worse? Maybe it's worse.
It's better.
It's okay?
Yes.
Okay, so if this is holomorphic, and then you have this condition that if the limit as z goes to a of z minus a times f of z, so if this limit was 0, then what we used in the Cauchy's integral formula, if you remember, we used that even if we don't know that it's holomorphic in A, we know that as long as this condition is satisfied, then the integral along a closed curve was actually 0. So this we used. And then I said also just orally that actually this is what's called a removable singularity, and it will imply that the function is actually holomorphic from the get-go. So then this is called a removable singularity. Okay. Yeah, so A is called a removable singularity of F. So, and this name of being removable is justified then by the following theorem. which is what I just said. So if this function is holomorphic outside of A, and it has a removable singularity at the point A, then actually F can be extended to a holomorphic function on U, on all of U. Okay, so an example would be something like sine z over z or something like that. Okay. When z is equal to 0, this would have a removable singularity. Okay, but we'll get back to that. So now I will have to be very careful about what I erase and what I don't erase. So let's just erase half the board at once to start the proof. Okay, so for the proof, okay, so actually the proof uses the following lemma. So we want to use the lemma, a lemma that says the following. And essentially all of the proof is just this lemma, okay? So we use a lemma that says that if F is holomorphic, on U minus A, and it's continuous at A, and F is holomorphic on all of U. So basically the point is this then, okay? So if it's continuous at A, then F is holomorphic on U. And as you will see, this removable singularity condition will then imply this. We'll be able to finish the proof that way. Okay, so the proof of lemma. So now I prove a lemma. It goes as following. So we consider gamma any closed path in U, and then we want to apply which theorem? Well, we want to apply Morera's theorem. So this is the idea. So we want to show that if this condition of a lemma holds, then actually the integral along any closed path in U is 0, and then by Morera's theorem, we're going to conclude that then F has to be holomorphic. Okay, so we have sort of two cases. So what are the two possible cases? If let me erase this now. So the two cases I will distinguish is that, so I have this gamma inside U, this path, and then the possibilities are that either A is, well, it could be inside, it could be outside, still in U, but it could also be on the curve gamma. So I will separate between the two cases that it's on gamma and that it's not on gamma, okay? But it could be outside. You're still here? Okay. So the first case is that A is not on the curve gamma. And remember, A is the point where I assume my function was continuous, okay? So this is the exceptional point where I don't know yet if it's holomorphic. Then we let CR be the boundary of the disk of radius r. So what we do is we take a disk as usual around this, and then we call, this, or we take a circle rather. So CR is this circle here, which is the boundary of the disk of radius r. And then we get that the integral, so we try to compute this integral, yes. So we want to compute the integral along gamma. So this is what we're doing. And we want to show that this one is equal to 0. So now what do we do? Well, we use the standard trick that you will remember from all this integration that we've been doing. Is that when I integrate along gamma, it will be the same as integrating along this this small disk, right? Because I can do this trick of adding this path on which I go once in this direction and once back. Okay. So if I orient this curve correctly, so then it's going to be equal to the integral along the whole of gamma. So again, this kind of thing is clear, right? If I just say it like that. So the statement is that this integral is equal to the integral along CR of z dz. Okay, and now this is true for any r. So then what I can do is I can let r go to 0. So I make this disk smaller and smaller and smaller. And this is when I use the continuity assumption, right? Because, okay, if really there was a singularity and the function went to infinity here, or had a very wild behavior, then we don't know what would happen to the integral, even if the disk was very small. But thanks to the fact that the function is continuous, when I shrink the disk, then the integral will actually go to 0. So then this one goes to 0. And this is by continuity. Okay, so this was the easier case, I guess. And the second case is what happens if if A is on the boundary of gamma. So instead of being there, it's somewhere here. It's on the boundary. So then what do we do? Well, then we simply try to take, then we simply try to avoid, so then we use this kind of continuity argument again. So then we try to avoid, so we modify gamma by taking a half circle going around here. Okay. And then we're going to use the continuity to say that actually going around like this on a very small circle is not going to change the value. It's going to change continuously the value of the integral. So what I'm trying to say is the following. So let me write down now what I meant. So we write gamma as the sum of some gamma tilde r as gamma r. So, okay, as in the picture, let's just draw it in the picture. So in the following picture, so I can do it on here. So let me make this drawing a bit more proper. So A is here. And then gamma tilde of r will be, how can I draw this? So gamma tilde of r will be everything going around like that, and then going like this, and continuing around. This will be gamma tilde of r. Of course, it depends on r because it depends on the radius of this small disk here. And then we need another color. Let's see where I put it. Here. And then the gamma of R is just going to be this small half disk here, okay? So it's just going to be this portion like this. And then when you sum them together, well, you're going to count this extra part twice. And if you orient it correctly, you're going to count it in different directions. And so the statement here, that gamma is equal to gamma tilde of R plus gamma of R is going to be true, okay? And then I'm going to shrink this thing again. Okay, so first of all, the first thing to note is that A is outside of the region defined by gamma tilde of R. So since inside now, so you see the inside of this gamma tilde of R, which goes like that. So inside here, then the function is holomorphic. The only bad point was outside, right? So then what it means is that the integral here has to be what?
The integral is going to be 0.
Because, yeah, because of this usual Cushy theorem here. So then the integral has to be 0. And the second thing, so moreover, if we look at the second piece, so now we look at this piece, gamma of R. So this one, what's going to happen? So this one is going to, again, then by continuity, this one is going to go to 0 as we shrink R to 0 by continuity. Okay, so in either case, the integral along gamma is going to tend to 0 as R tends to 0, but the integral of gamma is independent of R. So then there will be no choice but concluding that the integral of gamma is equal to 0, and this will be true for any curve gamma that I choose. So you see, we really chose any curve because we even allowed for this exceptional point to be even on the curve. So we even had to treat this case. And then we use Morera's theorem to say that since the integral was then 0 along any closed curve, then our function has to be holomorphic. Okay, so this proves the lemma. So it proves the lemma that says that if we assume continuity, apart from this being holomorphic, then F is holomorphic everywhere on U. Any questions about this before I erase it?
Professor.
Yes?
Which one is gamma R tilde? Perhaps I'm confused.
Yeah, it's not it's not a great notation. So gamma R tilde is the one that goes around like this. And then follows the small half circle and then continues. Is this
okay?
Is clear?
Yes.
Yeah. Good thing. Okay, any other question? Okay, good. So then let me erase this. So we proved the lemma. And now how do we go from the lemma to proving that if we have a removable singularity, then we are holomorphic? Well, then what remains to be done is okay. So it was clear the end of our proof that we applied Morera. So now we apply the lemma to some well-chosen function. And it's the following function. So g of z, which we define to be So as very often, we define it to be this z minus a times f of z, which was the thing that went to 0 when z tends to a. So this is how we define it if z is not equal to a. And if z is equal to a, then we let it be 0. Okay, so we define such a function, and then we apply the lemma to this function. And why can we apply the lemma? Well, this one is holomorphic outside of a, so multiplying by z minus a will mean it's still holomorphic outside, so in particular it's continuous. And by the hypothesis of being a removable singularity, it tends to 0 when z tends to a, so this function I defined is continuous, right? So so this is what I just said. So g of z is continuous. And is continuous on all of u. And by the lemma, this implies that g of z is holomorphic on u. And also, of course, g of a is equal to 0. So this extends to a holomorphic function on u with g of a equal to 0, which is because I defined it that way, right? So now we consider another function. So it's a sort of incremental construction. So we consider f tilde h, whatever we want to call it. But okay. Yeah, so I write f tilde because this is going to be the extension of f. So I wanted to call it f with some variant, right? So the restriction of this to u minus the point a is going to be equal to f. Okay, so how should we define this extension? So we had f that was defined except in this point a, and now we want to define an extension of f. So what should we do? And of course, the construction will use this intermediate step of g, but this is really the main step. To understand why we did this, you need to know what we're going to set here. So of course, with g of z, it's essentially equal to z minus a times f of z, right? Except of this 0. So what I want to do is I want to divide by z minus a here. So I set this to be g of z divided by z minus a. Z is not a. And then I want it to be, something in particular continuous. I will want this whole thing that's holomorphic. So then what should I set here? So when z is equal to a, what should be the value?
G prime a at a.
Exactly, because we have g of a is equal to 0. So here it says g of z minus g of a if you want. Just minus 0. So, let's see. And this is exactly why your answer was correct. That what we should put is g prime of z here. G prime of a. G prime of a. When z is equal to a. So because of this remark here, f tilde of z is continuous. I hope this is clear for everyone. I could just add this g of a since it was 0. So f tilde of z is continuous, and it is of course holomorphic on outside of this point a. So this implies now again we apply this useful lemma up here to conclude that f tilde of z is holomorphic on u. And of course, f tilde is equal to f outside of A. Okay, so it really is an extension of f, and it is holomorphic on all of you. So this proves the theorem that if you have a removable singularity, so if this limit here is equal to 0, then actually your function extends in a very elementary way to something holomorphic everywhere by putting exactly this. Okay. Questions about that? Well, I check the time. Okay, good. So then I erase it. Okay, so I said we had an example of all of this, and the example, I mean, there are many examples, of course, but I already wrote down sin z over z. So I think I will skip it for now, since we had so many technical issues that we're already very late for today. So you can read about it in the notes that I'll scan to you. Really, in case there are more technical issues, I should really scan these ones, send them before the lecture, so you could read them right now. Would have been useful. Okay, so the next thing that I wanted to do today, but we'll see now how much time we have, is to look at power series expansions of holomorphic functions. So what we want to show is that any holomorphic function can be expanded into a power series. Okay, so in other words, the goal of this section would be to prove then that holomorphic functions are analytic, and then we will no longer have this this ambiguity that Younes was talking about earlier today. So suppose that this function is holomorphic, and let us define the following. So what I'm doing now, just to let you know, is that I'm sort of, as a prelude to this this theorem that every holomorphic function is analytic, I'm just trying to show you how you can use these techniques from removable singularities to kind of intuitively understand why this should be true. I mean, you can sort of see how this power series expansion is obtained by the technique that we just used. So what I will do is this. So I introduce some function. Hello? So you see, this is exactly kind of a function that I used in the proof earlier. So I do this. So of course it's holomorphic on u minus a and continuous. This implies that it's holomorphic on u by this removable singularities theorem, or by this lemma that we had earlier, if you want. Okay. So now we write the following thing here. If we just rearrange these terms a little bit, it starts actually to look like a power series expansion. So if I moved, so if I look at z not equal to a, let's say, and then I move this to the other side, and then I moved f of a to the other side, we would get something like this. We would get this, but also by what I wrote over here, we know that f1 is holomorphic. So with f1 of z holomorphic, and f1 of A. So what is f1 of A? Well, it was equal to f prime of A. Okay, so it's holomorphic, and you have this condition. And now we repeat the process. So now we put f2, so we repeat the process using f1 instead of f here. So then we get f2 of z, which we define as f1 of z minus f of a, f1 of a, divided by z minus a when z is not equal to a, and we put it to be f prime, so f1 prime of a, when z is equal to a. And this, so what we get, well, then we get in the same way that this f2 is holomorphic, okay? So what we get is f2 of z f1 of z is equal to f1 of a plus z minus a f2 of z, with f2 holomorphic on U, and f2 of a is equal to f1 prime of a. And then if we want, we can also write f1 prime of a in terms of some derivatives of the original function f. What should it be, if anybody can see it? If you want to write this one in terms of derivatives of the original function f.
The second derivative of f of a.
Yes, but we also
Sorry,
need
second derivative of f at a.
We also need. Yes, but
We need what?
It will be equal to this. So f base of a, but we also need to divide by 2 in this case, but 2 is equal to 2 factorial, just to hint at the general expression. So why is this? So just to see, so differentiate. So f of z is equal, it was equal to this, right? So it was equal to f of a plus z minus a f1 of z. And then if you differentiate, then what we get is that f prime of z is equal to this. I hope you can see. And f base of z is equal to, so I differentiate this thing again. And this implies that if I put the second derivative and I plug in z equals to a, then this thing will disappear and it will be equal to 2 times f1 prime of z. So this will be equal to 2 f1 prime of a. And in other words, f1 prime of a is equal to f base of a divided by 2. So there is this 2 that comes in. I hope you can see this. Doubtful.
Yes, we can.
Okay. Okay, good. So now I erase this, because this was just a parenthesis in the proof. Okay, and so what we get. Okay, so we had f of z, we had this. F of z was equal to f of a plus z minus a times f1 of z. And then we plug in that f1 of z is equal to this business, and so on. So what we get is that f of z is equal to, so f of a, it stays, plus z minus a times all of this. So let me just write it then. That's this. So it's equal to f of a plus z minus a so f1 of a, right? But then the thing was that, right? Yeah, so f1 of a was equal to f prime of a. So instead of f of 1 of a, I write f prime of a. And then what I get is z minus a squared f2 of z. Okay. So I get this equality here, that f of z is equal to all of this business. And then I can repeat and I can continue developing this f2 of z. And what will happen is that, okay, then I will get here my f base of a over 2 factorial and then plus f3 and so on. And in the end, so by induction, you will be able to check that you get the following. So time to make slightly more space. So check that f of z is equal to exactly what you would expect. And so on, and on the nth place, so plus z minus a to the n, fn of z where fn of z is holomorphic on all of you, and fn of a is equal to the nth derivative of a divided by n factorial. Okay, so in the same way you get all of this. And it starts looking more and more like a power series expansion, right? Okay, so this is kind of an intro. So in fact, we get the following theorem. So in order, of course, to make this rigorous, so I'm trying to explain this just to give you some feeling for why one would, why one would think that holomorphic functions must have a power series expansion, or maybe, okay, this is common in real analysis, so you might try it anyway. But just to get a feeling for where this expansion is coming from. So this is one way of seeing it, but we will also give the rigorous proof and the rigorous statement of the following. So the following theorem would be that the slogan for this theorem would be that holomorphic functions, so complex differentiable functions, are analytic. So a translation of that would be that complex differentiable functions have a power series expansion of the recurrence. So this is the famous statement then. That holomorphic functions are analytic. And it goes as follows. Suppose f is holomorphic on some disk of radius r centered at A. Then f of z is equal to the sum of the nth derivatives in A divided by n factorial times z minus a to the n, where n goes from 0 to plus infinity. Okay, and this is true on this disk of radius r centered at A. Okay, so you get this expansion where the coefficients, the nth coefficient here is always given by the nth derivative divided by n factorial. Any question about the statement of this theorem? So actually, do you mind if we just finish the proof? It will take 5 minutes, and then at least we, we're not too far behind. Is that okay? Considering we had some technical issues, to say the least.
Yeah.
Okay. So let me do it then. So the proof. Okay, so I gave a proof assuming z is equal to 0, a is equal to 0, just for simplicity of notation, right? So if a is not 0, then you can do exactly the same thing, but instead of z, you will write z minus a everywhere. Okay. So let me just do this. And by Cushy's formula, so by this I mean Cushy's integral formula, gives that the integral, but f of z is equal to 1 over 2 pi I of f of w equal to this, where C is the circle here of radius r. Actually, we will have this picture slightly more. So C is the circle of radius r0, okay, which is equal to then circle of radius r0, and then we take some intermediate, and all of these are inside the even larger circle, right? So we have here in the middle A, then we have radius r, then we have radius r0 in the following way. Okay, and z is somewhere inside here. What is z? Okay, yeah, so z, let's take z inside here. Okay, so yes, okay. Yeah, so r is taken, sorry about that. So r is taken to be the absolute value of z. Okay, so then let us recall that. So we want to get the power series expansion out of this kind of thing. And how do we do that? Well, what we do is that we note that this factor 1 over w minus z, well, this has a sort of well-known expansion, because we can use the trick that we factor out this 1 over w. So we write it as 1 over w times 1 minus z over w. And then we note that this is equal, so let me erase for it. So this 1 over 1 minus z over w, so this is something that you recognize, right? This kind of expansion. So you know that this thing here, it will be equal to the following. Following thing, right? So this is classical, if you just put z over w as your variable now. And this converges. We have to be a bit careful, of course. But this converges as the absolute value of z over the absolute value of w. This is equal to r over r0, which is less than 1. So z was on this, this is z, and this is w. Right? So the absolute value of z is smaller than the absolute value of w. So this is then convergent. So it is moreover, so even stronger than that, it's actually uniformly convergent. And why do we want that, by the way? Well, we want it because we will want to interchange the limit and the integration here. Okay, but so can anybody tell me why it is uniformly convergent, this thing? So there's a result that we haven't seen in a few weeks. So the reason is that all of a sudden this Weierstrass M-test comes back. Okay, so you recall that if you have the sum, if you look at the sum of some function, so fn of z, and you have that the absolute value of fn of z is less than or equal to m times an, where the sum of an are convergent, then also this sum converges uniformly, right? And in this case, well, we apply this fn of z to be this z over w to the power n, and since the absolute value of z over w is less than 1, this m-test applies. Okay, so we get this uniform convergence. And this means, by a well-known fact, that if you have uniform convergence, you can interchange limits and integration. So what we'll do okay, so f of z is equal to, so let's recap what we had. Equal to this, but this one I could write it in the following way, right? Because I had this 1 over w minus z, it was equal to all of this. So 1 plus z over w and dw. Now I interchange the limit. So this sum has a built-in limit in it, right? So interchange the limit with the integration, and I get that this is equal to the sum of the integral over c. So I could put the 1 over 2 pi I somewhere, put it here. So it's f of w divided by w times z over w to the n, okay? But this w to the n that I have here, I put it here. So I take it n plus 1. And then the z, so this integral is over w, so the z I might as well put it outside, okay? So I can write it like this. And now this is again something that you recognize from the Cushy's integral formula. So by Cushy's integral formula, it would have an n factorial here, and then it would be equal to the nth derivative. So this one is equal to the nth derivative, but divided by n factorial times Z to the n. Okay. This is what we wanted to prove. Okay, so it wasn't harder than that, after remembering Weierstrass M-test, to prove that any holomorphic function is uniformly convergent. Sorry, that any holomorphic function has a power series expansion. Sorry. Okay, so the picture is something like this. So this is U, and then maybe it has some part inside where the function is not holomorphic. So let's say that f is holomorphic on all of this, but not on this little hole. And maybe there is some singularity here or something. And then assume that I take my point A, and I want to ask about the power series expansion about this point. Then what will be the radius of convergence of this? So I know I got a question about this at the end of the other lecture. So what it means is you can take the power series expansion, okay, which converges in some disk around here. But the question is, can we see even from the picture what will be the radius of convergence of this thing? Any ideas? If you can see the picture. Are you guys still there?
What's the question?
So the question is, what will the radius of convergence be here in the picture? So I said I drew this picture of some domain U, but which was not simply connected, for example, or there was maybe some singularity here, or I mean something like that. Let's say it's not simply connected. So if it's holomorphic on this domain, but not here, and not outside, then what will be the radius of convergence of this power series expansion that we just proved?
It's the distance from that point to where it ends, to where the U.
Exactly. So to the nearest point where the function is no longer holomorphic, right? So yeah, so I got a question about this some other time. So the power series expansion around A will then converge in this disk. And the slogan is sort of at the power series. So I will write this and then I will end, I guess. Power series expansion of F around the point converges up to the nearest point or the nearest place where F is no longer holomorphic. And so this is very useful, right? So this means in particular that you don't, I mean, if I ask you to give a power series expansion of a holomorphic function, as I did in some homework, then it's not necessary to always compute it by force, you know, by this root test or ratio test. But if you know the function and you know that the function maybe has some branch cut somewhere or so on, then you can just see what is the biggest disk I can fit in there, and the radius of this disk will actually be the radius of convergence.
Professor.
Yes.
But this is just for convenience, right? It's, I mean, if we, what I'm saying is it could still be holomorphic outside of the disk, right? In this case.
Absolutely. So in this case, it is. So this is this thing called.
Sorry, I mean, it could the power series could still converge outside the disk. Is that possible in this case?
No. So this particular power series, I mean, yeah, I mean, this is the largest disk where it converges in some sense. Then, if you want to continue, you usually take a new point inside this disk. You know, a 2 or something, and then you take another disk where it converges, maybe it's here, your A2, and then it converges in this disk, and then you take another point and it converges in this disk, and then you get this thing called analytic continuation.
I think he meant that the powers expansion could be bigger, could have a bigger radius of convergence.
Right, because the only obstruction here is just that it's the obstruction is on the one side, right? So it could still I don't know.
It's like an analytical expansion or something.
Yeah. No, I understand what you mean. You mean that it can be you can go far in this direction, but not in this direction. I understand, and that's right. Yeah, but but technically speaking, the radius of convergence is when it's a disk, so it's not some other shape. This is
but sometimes even a disk, it could be bigger.
No, I mean the disk couldn't contain anything out here. If we assume
because maybe the function is not defined on that, but it's analytical.
Yeah. No, so if this was a removable singularity inside here, then yeah, it could be bigger.
Perhaps what I'm asking is this: if it was a rectangle of convergence or something like that, we could get a bigger domain where. Okay.
Exactly. So if it was a rectangle of convergence, you could get the bigger domain, and if this picture allowed for this empty part in the middle to be a removable singularity, then you could get even a bigger disk. But now the picture was supposed to be that here you really have some reason why you cannot define it.
No,
thank you.
No, but I think if it has a radius of convergence that stops there, then even on the other side you can't have it. It's not gonna be defined. You'll have to find another power series expansion.
What do you mean? I mean, so if you computed the radius of convergence and it really did stop there, then it means you cannot extend it to be holomorphic.
Yeah, even on the other side, you can't extend the power series.
Yeah.
Yeah, because if it's radius of convergence R, then every Z, such as the norm of Z is bigger than R, it's gonna be divergent. You'll have to find another power series on the rest of the domain.
Yeah,
you might actually be right in that. Yeah. But so anyway, so this technique anyways that you usually use is exactly what you said. So it's this analytic continuation that you take another point and then you continue with disks around and around until you cover everything. And so what is true is that if you have two power series expansions, so and they are power series expansions of the same function, then it means that these expansions, they coincide on some open sets, okay? Then actually the functions that they define have to coincide everywhere. But you're right that the expansion might not be the same, so to speak. So this is so actually this is something that I wanted to cover today. But so let me just write it down and ask you to maybe read it in the notes. So I will, when I send you the notes and copy them, I will copy also this part, even though we didn't talk about it. So the identity theorem, it says that if you have two holomorphic functions, f equals g. So for example, if you have two power series expansions defining holomorphic functions, and they coincide on the overlap on these disks of convergence, if they coincide on some open set, some open connected set, okay. Then f is equal to g everywhere, or some open set, and then they equal everywhere on the connected component of this set where we overlap. So it's just this slightly technical condition, but only connected component of U. So okay, I call it U, the set where they are equal, which is not supposed to be the same. So on some set B, maybe, then they coincide everywhere on the connected component of B inside of U. So actually, it's kind of not good that we started having all these problems, and I didn't get to talk about that, which I normally would have had time to do on a blackboard and so on, where everything worked well. Because for one of the homework exercises, you need exactly this theorem, right?
Yes, and Professor, I have one question. If suppose f is entire,
yes,
and g is not entire, but it is equal to f in some domain,
yeah.
Then what I wanted to ask is, will the power series well, f can be does that mean there is some relation between the power series as well?
So the first question when you say this is, can this even happen? So if f is if f is entire, so it's holomorphic everywhere in the plane, and then you have some other holomorphic function which is equal to, which coincides with f on an open set. This is what you're saying, right?
Yes.
Yeah, so then in that case, f minus g's should be, so they are 0 on this open set, but then they should be 0 everywhere where they are defined, right?
Yes.
So it means that they are equal not only on this small set that you might have found, but they should be equal everywhere. So unless I'm missing, are you going to tell me that G is not defined for some bizarre reason somewhere or something? But apart from that, they should really be equal everywhere.
Right.
It's
what I wanted,
of course, a reasonable function.
Right. What I wanted to know is if I compute a power series expansion for the entire function, will that also work for, because it's defined everywhere? I don't need to compute the power series expansion of an entire function everywhere. I just can compute it at 0 and just take it as the definition. So will that also work for that function z on that on the set where they are defined?
For function g, yeah. So so any function that is wherever g is defined, it will be equal to f if they were equal on some open set, right? Or even on some, not even necessarily on an open set, but just they are equal on some set with accumulation points actually. So you can read this. So then in particular, the function is equal to its power series expansion if it's entire, right? And it's valid everywhere.
So what I guess I'm asking is this: if say there is some neighborhood of the origin where f and z are equal, and f is an entire function, so I can take its still power series as to be its definition. So if I compute a power series of z at the origin, then will it equal the power series of f? It should not, intuitively, I think.
So you're saying that the functions are equal, but their power series are different? So of course, if functions are equal, the power series expansions must be equal, right?
Right. Yes. But okay, maybe I'll formulate my question better next time.
Okay. Yeah, maybe I didn't understand. But anyway, so please, after this, I'll scan it after lunch and so on. But this identity theorem, it looks like that. You can see it. So this theorem you need to use for your homework. But I think you're capable of reading this in advance and still handing in something. It's not super important. But just so you can have a look at it, since unfortunately, it's kind of a mess right now, all this teaching, all these problems that we had, technical problems, we've never had them before, right? So really, I apologize for that. on the behalf of ICTP, I guess, but not so much to do. Okay, so any other questions? Are you all in your rooms all day now? You cannot come to ICTP, or how's it going?
Fine.
Sorry? Oh, by the way, I see that it's past 1, so we should really go eat, I guess. I guess you also have cafeteria times, maybe, that you need to keep.
Yes.
Yes. Okay, so if there are no more questions, then let's have lunch, and let's, yeah, since it was so terrible this time with the iPad that half worked and then some weird angle on some Blackboard, yeah, let's go read the notes that I send you as well, okay? So I'll send them to you after lunch, and then we'll meet on Wednesday and hope that the technology is friendlier and that they resolved everything after this. Okay. And yeah, and on Wednesday then I will want the homework if that's all right. I hope that works.
Thank you.
Okay, thank you. Bye. See you.
Right.